Hey guys, Ms. Peterson here, and welcome to our chemistry lecture on chemical reactions. In this lecture, we're going to be going over how to read a chemical reaction, what the reactants are, what the products are, and show you two methods that you can use to balance those reactions. So, what even is a chemical reaction? Well, a chemical reaction is just a representation of the chemical bonds that are being broken and formed in any sort of change. So if we look at this one, which is the combustion of methane, we see the CH4, the carbon represented by the yellow sphere, bonded to the 4 hydrogen, reacting with two O2s, okay, 2 oxygen atoms bonded together. Now, those chemical bonds between the carbon and the hydrogen are breaking so that it can form the water. The hydrogen is rebonding to the oxygen atoms, and some of the oxygens are rebonding to the carbon. It's a chemical reaction. So when we talk about our chemical reactions, the things on the left side of the arrow are called our reactants. Okay, they're what you start with. In this case, it would be the CH4, aka methane, and the 2 moles of O2, aka oxygen gas. Okay, and if you don't know what it's called, it is totally fine to just use the chemical formula. Where the stuff on the right side of the arrow are your products, okay? That's what you make after the chemical reaction. In this example, the CO2, carbon dioxide, and the 2 moles of H2O, aka water. Okay, so these numbers out in front, those 2's, are called the coefficients. And with our chemical reactions, like if you were reading a recipe, you wouldn't read in a recipe, please add 2,502 grains of sugar. Okay? We don't count sugar in grains of sugar. We don't count atoms in atoms or molecules. We count them in moles of atoms. Okay? So the coefficients represent the number of moles of each of those compounds involved, because that's how we count atoms. So this reaction would read that the methane, there's an invisible one there. Okay? If there's no coefficient, there's an invisible one. Chemists don't like to write ones. So it reads 1 mole, or methane, reacts with 2 moles of oxygen to produce carbon dioxide and 2 moles of water. Okay, cool? Okay, cool. So what about phase symbols? So if you look at these two reactions, those bolded parts that come after the chemical formulas are called phase symbols. And they tell you the phase of that reactant or product. So S is for solid. So this reaction reads that solid aluminum reacts with the copper chloride. Okay? L is for liquid, and G is for gas. Makes sense, right? But then you're probably wondering, what about that AQ? Now that AQ means aqueous. It means dissolved in water, okay? Water is our universal solvent. Like our body is like 70% water, okay? A lot of the environment has to do with water. So a lot of chemistry just happens in water. So we have a special phase symbol, AQ, meaning, hey, there's water around when this reaction is happening. Okay, cool. So how and why do chemical reactions happen? We're going to go ahead and flip over and look at a very simplified image of what's going on in a chemical reaction. So this is the FET reactions and rates. You can see the reaction right here. The A, represented by this yellow sphere, is reacting with this BC molecule to form AB, so the yellow bonded to the pink, and leaving the C by itself. And then we have this, which is called the potential energy diagram for this reaction. So I can try to get these to go by pulling back that and letting it go. Now, is the reaction happening? No, they're just bouncing off of each other. This green line represents my total energy, okay? So when molecules react, they do need to bump into each other, but they need to bump into each other with enough energy to overcome what we call the activation energy. So I'm going to raise that temp up until it's all the way over here. And now we see that reaction has happened. And we'll let it go, come back and react once again. They collide. The yellow bonds to the pink and leaves the blue by itself until that collision happens again. Now I'm going to go ahead and pause it for a sec. And I want you to picture what would happen, you think, if this yellow were to instead collide with the blue end of it. Would a chemical reaction still happen? Could we still form this AB molecule? No, okay, because they wouldn't be in the proper orientation. Okay, so it has to have enough energy and be in the proper orientation. And that is called, collision theory. Okay, collision theory states that in order to react, the reactants must collide with enough energy and in the proper orientation. That amount of energy that they need is called the activation energy, which we normally abbreviate with E sub A for energy of activation. And then we'll represent that in a reaction diagram like you just saw. So you can see we have energy up here on the y-axis. We have the reaction coordinate on the x-axis, meaning this bottom line represents the energy of my reactants. And then this line on the right side represents the energy of my products. Okay. Now the energy that you need to put in to get from the reactants to the top of this hill, that is the activation energy. Okay, cool. Okay, cool. So what about balancing chemical reactions? This has to do with the law of conservation of matter. Okay, we can't just have atoms or moles of atoms appearing and disappearing in these reactions and changes that we're representing. We want to apply the law of conservation of mass and make sure that the number of moles of each type of atom is the same on both sides of those equations. So we're going to manipulate the coefficients, not the chemical formulas of those compounds. And I'm going to go show you guys two methods, the block method and the count or the tally method. And you guys will be able to determine which one makes the most sense in your brain. So where an unbalanced reaction might look something like this, where here we have that Cl2. That's 2 chlorine atoms. Where on this side we have Cl3. That's 3 chlorine atoms. So that's not balanced. It's not equal. Where if we balance that reaction, we end up with 3 Cl2s, which is 6 chlorine atoms, and 2 Cl3s, which is also 6 chlorine atoms. And that's the balanced chemical reaction. Now, if you in your brain can look at a reaction like this and be like, okay, AlCl3 and Cl2, so we're going to need to put a 2 there and make those both 6. But then that gives me 3 coppers, so I'm going to need 3 coppers on that side and 2 aluminums, so I'm going to need 2 aluminums on that side. That's balancing it in your head. And if you have a super mathy brain, go for it. Okay, good for you. If you have a less mathy brain, I'm going to show you some tricks for that. So the first one I'm going to show you is the brick method. And I don't have any polyatomics here, but if I did, you would count them as one element when writing those chemical formulas. So when we are using the brick method, what we do is we treat the arrow like a dividing line, okay, down the middle of our page. And then we have bricks representing each of our compound. So we have this C2H4. So we're going to have C2H4 bricks. And C2H4 bricks are made of 2 blocks of carbon and 4 blocks of hydrogen. Okay, 2 carbons, 4 hydrogens is my CH4. I have my oxygen bricks, which are O and O. And then on my product side, I have my carbon dioxide bricks, which are a carbon and 2 oxygens, and my water bricks, which are 2 hydrogens and 1 oxygen. Okay, so you do 1 brick of each element first. And then we're going to cancel out things that are the same on the reactant side and the product side, kind of like math class and crossing out things that are the same on both sides of the equation. So this carbon can cancel out with this carbon. These two hydrogens can cancel out with these two hydrogens. And then two of my oxygens can cancel out. But I still have some carbons and some hydrogens on my reactant side and some oxygens on my product side that aren't canceled out. So I'm going to need to add more bricks. First, to cancel out this carbon, I'm going to go ahead and add another brick of my carbon dioxide. I can't just add the carbon. I don't have any of those bricks. I only have carbon dioxide. So I'm going to add it as that COO. And that allows me, I'll switch to orange so that you guys can see this in order. So then this carbon can cancel out with this carbon. I'm going to go ahead and deal with my hydrogens too. So I have two hydrogens here. So I'm going to do another H2O brick over here. And then we can see that these two hydrogens will cancel out with these two hydrogens. But then I still have 1, 2, 3, 4 oxygen atoms, okay? So I'm going to need to add 2 more bricks of oxygen, okay? And that will allow my 4 oxygen atoms, 3, 4, to cancel out with these 4. 1, 2, 3, 4. And now everything is all canceled out. Once everything is all canceled out, your coefficients are going to equal the number of bricks. So we'll have an invisible one there. Okay, O2 will have a 3 in front of the O2, a 2 in front of that carbon dioxide, and a 2 in front of that H2O. And now we have 2 carbons, 2 carbons, 4 hydrogens, 4 hydrogens, 6 oxygens, 2 plus 2 times 2, so 4, plus 2 oxygens, and we're balanced. Okay, cool? Okay, cool. Let me go ahead and show you guys another method to balance that same reaction. So this is called the count method or the tally method, however you want to look at it. But for this one, what we do is we write all of our atoms involved down the center of the page. And then we do a tally for how many we have on each side. So right now I have 2 carbon atoms on my reactant side, 4 hydrogen atoms, and 2 oxygen atoms. Where on my product side, I have CO2, that's 1 carbon and 2 oxygens, H2, so 2 hydrogens and 1 oxygen for that H2O. And then we can see that it's not balanced. So this reaction is a little bit more guess and check. First, I'm going to try to deal with my carbons and put a 2 in front of that CO2. That gives me 1 more carbon, which balances out my carbons, and 2 more oxygens. So add those 2 more oxygens. Okay. And then I go down to my hydrogens. Okay. For the hydrogens, I have 4 on this side, so I'm going to put a 2 in front of my H2O, which takes it to 4 total hydrogens on my product side and adds another oxygen. Okay. So now, okay, I added another H2O, 2 H's, 1 O, and now my hydrogens are balanced. So now I'm down to my oxygens. And for the oxygens, I have 1, 2, 3, 4, 5, 6 on this side. So I'm going to put a 3 in front of that O2 to make it 6 on that side. And we have a balanced reaction. So that's the tally method. So how did the methods compare? Which one did you like better? How are they similar and different? Okay, pick what you really like and get some practice balancing those reactions. Okay, cool. Okay, cool.